In this section we're interested in when a body is either suspended from a point or it's placed on an inclined plane and then the plane is tilted further and further until potentially the object topples. We've already met the idea that if we suspend a shape from a point, then the centre of mass will lie directly below the point of suspension, as shown here. What's quite common in a problem is that some point is chosen on the shape, say for example a point N, and we have to find a specific angle that perhaps in this case the line OG makes with the downward vertical. Don't redraw the shape to try and draw it in the right orientation. Instead, draw a straight line that passes from the point it's suspended from, in this case I said N, that goes straight down through G, make that the downward vertical, and then you can clearly see that the angle theta would be the angle that OG perhaps made with the downward vertical. Okay, if we place things on planes, the first thing we've got to do is assume that the plane is rough enough to prevent slipping from occurring. Now, if you look in the first case, what we can see is that the line of action of the force actually lies within the contact surface between the shape and the plane. In that case, there are no moments here, there's no toppling moment, and so the object will stay where it is, as long as it's rough enough, of course. Now look at the second case, and this time you can see that the line of action of the force acts outside the surface contact of the shape, and so the point A will actually act like a pivot point, and the shape would topple over about point A. It should be fairly clear that the critical position would be when the line of action of the weight actually would pass through, in this case, the point A, and that would be our critical case, and that's where we normally have to solve problems. So let's have a look at a question. The first thing I'm going to do is take this shape here, and I'm going to find its centre of mass, and then once I've done that, we're going to put it on a plane and see how far we can tilt the plane upwards. So the first part of this should be fairly standard. I'll modify the diagram a little to begin with. I've marked on a x-axis and a y-axis, and I've marked on now for the two separate shapes, as I'm going to consider this, the points A and B, which are where their respective centres of mass would appear to be. This is just pure calculation. You can just watch this and follow it through. So I'm going to find the weights of the two shapes. I'm going to locate where the centres of mass are using my axes, and I end up with this. That can be simplified down. Have a good check and make sure that you're happy with what I've put here. Now in a second I'm going to do the moments equation, but first of all I'm just going to look at the weight ratio to perhaps simplify the equation a little. And so I can see in fact that the weights are in the ratio of 4 to 3 to 7, and so now I can form my equation. So taking moments, and I will end up with the equation like this. A little bit of simple expansion will give me the following, and then I can clearly see that x bar is equal to 26 over 7 and y bar is equal to 18 over 7. Right, in fact this is what we're going to do. We're going to put our object on a plane as shown, and we're going to find what the maximum value alpha is until this shape topples. So what we're going to do is we're going to consider when it's on the point of toppling, and at that point in time the line of action of the weight would actually be passing directly down through P. Now what you'll see in this example is just a little bit of geometry, but the geometry is essentially the same for any problem of this nature, so do make sure that you follow what I do. So I drop the line in first, as shown. The centre of mass is located. I make a right angle triangle, as you can see here, and alpha is the angle I'm after. So what I'm doing is I've labelled the other angle in the bottom triangle as beta, and then just using the vertically opposite angles from year 9, I can see that other angle will be beta, and of course if these are both right angle triangles and that's beta, then the top angle must also be alpha. Fairly easy to see. Try it with numbers if you're a little bit unhappy with using the letters, and you'll see that that is indeed the case. Well, what I can now do is note that that's y bar and that's x bar. My job is to find alpha, and in fact what we'll do is just consider the top triangle, and I can now say that the tan of alpha is opposite over adjacent, y bar over x bar. Throw the numbers in, and then eventually just use my calculator to find that the angle in question is 34.7 degrees, and that's the limiting case. Any more than that and the thing will topple. So it's in limiting equilibrium there. Okay, let's look at another case, another question. It looks a little bit more complicated, this one. I mean, in fact, it's very, very easy. Again, what I've done is I've drawn on a pair of x and y axes, and these distances A and B are going to be where the centres of mass of the semicircle would be in the triangle, if I consider this as two separate shapes. Obviously, because of the symmetry of the problem, the y coordinate of the centre of mass will actually lie on the line, what is it, BD. Okay, so I need to do a little bit of side work this time. I think the first thing I'll do is just consider the weights. I'll do it straight away into a ratio, and I'm just using standard formula here. So I'll pause there, and so I've got a semicircle with a radius of 2, so pi r squared over 2, W, and to give me the weight per unit area, so the overall weight. The triangle will be base times height divided by 2, so 4 times 3 over 2, divided by 2, W, and then the composite shape at the end. I won't bother writing that in on the first line, I'll do the working out. That simplifies to be 2 pi to 3, and therefore if I add them together I get 2 pi plus 3. The next job is to find where the centres of mass of my two shapes are going to be, and these are really just standard formulae. If you look back in your notes, you'll find the centre of mass of a semicircle, which I did advise you to learn. In the formula booklet in the exam, you're actually given the formula just for a sector. Okay, so here we go. The formula is 4 over 3 pi. So if I put in the radius, I get the coordinate as minus 8 over 3 pi, and the y coordinate is 0 as discussed earlier. And for the triangle, it'll be a third of the way along the median line. Sorry, a third of the way along the altitude. So in that case, it will be half a third of 3 over 2. Okay, so far so good. We can now simply take moments. So I'll do that on a new slide. Taking moments. Throwing all the information together, we get this. It looks a little cumbersome, but it simplifies down quite nicely, as shown. Another line of working will give us this, and finally we get x bar is equal to minus 23 over 6 parenthesis 2 pi plus 3. And if you work that out, you actually get minus 0.413, so the centre of mass lies in the semicircular part of the shape. But it only wanted the distance from AC, so the answer would be 0.413. Now, in further calculations, of course, I'm going to use the accurate answer, which I've still got on my calculator, from the minus 23 over 6 parenthesis 2 pi plus 3. I checked the answers in the book. This is a question from the book, and in fact they used a rounded answer, which is wrong, of course. Nonetheless, let's do the next part. So we're now told the shape is suspended from the point A. So I've drawn in the downward vertical, and we had to find the angle that the line AC made with the downward vertical, and it should be fairly clear what to do here. Tan theta would equal x bar over 2, so I can put that in, and the answer simply comes out to be 11.7 degrees. Therefore, to the nearest degree, the answer is 12. And then for the final part of this question, we're told that now a mass is suspended from D of kmg, and such that BD is now going to be vertical. BD will now be horizontal, as shown. So this is really just an M1 question about taking moments. So if we put the point F in and we take moments about F, then we can say that the clockwise moment must be equal to the anti-clockwise moment, as shown. A very, very quick and simple bit of simplification gives us that k is equal to 2/3 of x bar, which gives us k is equal to 0.275. And that's it. Watch this a couple of times if needs be. By all means, work through the problems on a piece of paper as you're going along, but you should see with a little bit of care and attention to detail, the problems are in fact very, very easy indeed.